In the screencast, we're going to look at the big picture for our Module 3 material, which is the carbon-carbon bond formation via substitution at the alpha carbon. So what are the functional groups containing alpha carbons that we're going to be interested in? So I'm going to draw a pretty general structure at this point that contains a carbonyl. To the right of it, I'm going to call that an R group, and then I'm going to extend off the chain to the left, and at this point identify some features of this structure, namely the alpha carbon. That's what we're mainly interested in for this module, is a carbon right next door to the carbonyl group. And then we continue with the Greek alphabet. The carbon after that is beta, and then the carbon after that is gamma, and then finally delta, and so on and so forth. So what are the R groups that we're going to be concerned with? What are the functional groups? So if R is hydrogen or carbon, we have an aldehyde or a ketone. These are going to be oxidation state 2 functional groups. Keep in mind that only the ketone really can have a different alpha group, alpha prime, if the molecule is not symmetric. If the R group is H, then there is no alpha carbon. Alternatively, we can have oxidation state 3 functional groups. If R is OH, that's an acid. If it's OR1, that's an ester. Or alternative, we can have the amide functional group, and again, those would be oxidation state 3 functional groups, and they will only have one alpha carbon. So really, the ketone is the one you have to be concerned about. We'll write may have alpha and alpha prime if the molecule is unsymmetric. So we're concerned with the alpha carbon. This particular alpha carbon has 2 hydrogens. We are going to examine both basic and acidic conditions. To generate a nucleophile. For the following reactions, under basic conditions, we will generate an enolate. Under acidic conditions, we generate an enol. So for the purposes of this screencast, we're just going to draw the enolate structure. So again, terms that end in ATE have negative charges in them. So we're deprotonating the alpha position. And this species here is called an enolate. The enolate, again, is the nucleophile. That's the reactivity. It is supplying the electrons to form the bond. And again, over the course of this module, we're going to look at different named reactions to form carbon-carbon bonds. And the named reactions are based on the electrophile that's employed. So I'll show 3 examples here of electrophiles based on the starting oxidation state. So in the first top example, if we were to use the following electrophile, say 2-iodopropane. The carbon bearing the halogen is at oxidation state 1. And this would undergo an SN2 reaction mechanism where the nucleophile attacks the carbon bearing the halogen, displacing it to end up with the following product. So here was our original alpha carbon, beta, gamma, delta. Now we've formed this new bond right here. So we also have now a new beta prime. So in these reactions, we're always forming a new bond between the alpha carbon and the new beta prime carbon. If we look at the oxidation state of that beta prime, it started at, originally in the electrophile it was 1, now it's at an oxidation state of 0. So overall, this has been a reduction. And we will see that with the subsequent electrophiles that we use. The next reaction, if we were to employ, say, an aldehyde, or alternatively a ketone, the carbonyl is at oxidation state 2. That electrophile is going to undergo nucleophilic addition. So we've seen that in reactions already this semester. So we draw our original carbon backbone. We'll put in alpha, beta, gamma, delta. Again, the new bond we are forming is here. The electrophile at oxidation state 2 becomes oxidation state 1. And we fill in the rest of that chain. So now we have beta prime and gamma prime. The carbon that was attacked now is at an oxidation state of 1. And again, this is the new bond that we just formed. So we've gone from oxidation state 2 to 1 using nucleophilic addition to the carbonyl. We're going to now move up an oxidation state and look specifically at an ester. We're starting at oxidation state 3. The nucleophile will attack that carbon, doing a reduction. So the mechanism by which this occurs is nucleophilic acyl substitution, which we've seen already this semester. And again, the product of this will be the following: alpha, beta, gamma, delta. The new bond we form is here. We're doing a reduction, so the ester now becomes a ketone. We put in the rest of those carbons. We have beta prime, gamma prime. Now the oxidation state at beta prime is 2. And again, this is the new bond we formed, C alpha to C beta prime. So all of these reactions are reductions in regard to the classification of the starting electrophile. If we start at 1, we proceed through an SN2 reaction. If we start at 2, nucleophilic addition. If we start at 3, we have nucleophilic acyl substitution. So throughout the course of this module, we're going to look at what bases we need to use to deprotonate the alpha carbon to form the enolate. Alternatively, if we're under acidic conditions, formation of the enol. and then the various electrophiles that we will employ to do substitutions at the alpha position.